Hello, recently I've been quite interested in the binary system and how it can be used inside of games. In this video we'll be discussing the possibilities of binary and logic inside of Minecraft and creating a CPU. Firstly we'll look at the game, afterwards we'll check out the planning for the computer, and finally we'll inspect the CPU and its parts. To start off, we'll quickly look at all the parts of what redstone is. First we got the redstone dust itself. It can be powered and then it decays until the single strength is no more, and then it won't power anymore. Then we got the repeater. The repeater just reinvents that signal basically. So if we power it again, we got a single strength coming in, and then we got a 0. This one isn't powered because nothing is powering, and then it's back to 50, and it can keep going for 15 blocks again. Then if we power through a block, nothing will happen because it's powering the block but it's not strong enough to pass through. We can use a repeater instead, then it powers the block is extra powered and it can be taken out. That's the same with this one. It's powering it, the repeater is strong enough to take it out and power the lamp. We can see that over here. Then we got the inverter. This is our first logic gate. The truth table of that is very simple. If the input is on, the output is off. If the input is off, the output will be on. We can see that over here. If I flick this lever, it will turn off, and if I turn it off, it will turn on. Then we move to the comparator. A comparator is a very specific component. It can have inputs from the back and sides, and it has an output from the front. It puts out the same single strength as has been put in. So 14 has been put in, 14 has been put out. Here again, if I power it, 9 has been inputted, 9 will be outputted. But it has side inputs. If I now power the side input, it will be smaller then, because it's 6 than this one, and nothing will happen. However, if it's bigger than the back input, it will cancel it. So now it's 12 and 9, so it will cancel it. And then we have another mode, it's called subtract mode. Well, you already guessed, if 6 is going in from the side and 9 is going in, the output will be 3, because 6 minus 9 is 3. Then we got the AND gate. The AND gate will only turn on if both inputs are turned on. So we can flick this, nothing happens. We can flick this, nothing happens. And both they are on. This uses two inverters that are ORed together into another inverter. The OR gate as well, XOR gate as well, is a very useful gate. It only works if one of the two inputs is on, not both or not either of them. It's turned on, it's turned on. However, if both are turned on, it turns off again. This uses the subtract signal. For 14 minus 14 is 0, and 14 minus 14 is 0 as well. If only one is on, it's 14 minus 14 is 0. However, now it's 13 minus 11 is 2, so something goes through. Secondly, we'll talk about the layout of the computer real quick. This is the main computer. Then we got the control unit over here, and then we got the wires. We'll start with the wires. The wires connect everything. It's very easy. With the clock, we got a clock. A clock is something that pulls constantly. That goes into a program counter, and the program counter decides which instruction should be written to the computer. Then we got the two instruction lines. For the computer itself, it has inputs, then a register. The register stores the information needed for programs. It just stores data. Then we got our ALU. The ALU is the most important part of the entire computer. The ALU does the simple arithmetic operations such as add, subtract, and, or. It does all kinds of stuff. It's very useful. The output of the ALU has been wrapped around back into the register. For example, if you want to do 1 plus 1 plus 1, well, the ALU can only do two things at a time. So it adds 1 plus 1, it goes back to the register, and then it does the 2 plus the 1 equals 3. And then we can decide to get it to the output. We got a number display and an XY plotter, which is basically a screen. Okay, now let's start off with the actual computer. I'm currently standing on it. This is the entire computer. Well, let's start with the registers, because it's the easiest of the entire computer. It's a bit difficult to see, so we'll move on to the remote one over here. So how does it work? Well, here I've got one singular bit of the registers. How it works is this one is constant. Okay, let's see. I can power a repeater, of course. And I can power it from the side, and then it will get like a box on it. And look what happens if I disable the input. It remembered its state, which is very useful if you want to store bits. So yeah, this is basically the entire part of storing it, and we also have the part afterwards, which is a comparator on subtract mode. And if I power it, the signal will be blocked because 15 is being put in and 15 is being put on over here, and 15 minus 15 equals 0. So we can block the signal, and if we unpower it, so now we have now can write the signal. Now if we stack this up 8 times, because we're working with an 8-bit computer, if we stack this up 8 times, we get one singular byte, one slice. What we can do is we can put some data in it, for example a 5 in binary, and we can just press this button to write it. So I write, and you can see here it has been stored. This one is powered and this one. We can unpower them and see they're still being remembered. And then over here we got the write button, the read. And now we can see the 5 is being written, and we can disable it again. Very cool. Now if we stack this 8 times, we get a register file. But notice there are 16 bytes over here instead of 8. I thought we wanted 8. This is true because we also need to sometimes we need to read 2 numbers at the same time, because an ALU, a computer, for example, if you want to add 2 numbers, you need to be able to read 2 numbers at the same time. So that's why every single register is cloned. So this register is the same as this one, but they can be addressed individually. So we write the same number. So if I write a 128 to register 2, in this case it is stored there. It's stored in both registers, but I can read them separately. So for example, I can read on this side, I can read this one, and on this side I can read this one, for example. So I get 2 different numbers which I can add with the ALU, and we'll go there right now. So here it is, located inside of a computer, right behind the register. So we can see the output of the register has been put into the ALU, and we can also move to a separate version of it, so it's easier to explain. Well, first let's talk inputs. We got the 4 purple inputs at the bottom. What this does is it chooses the operation you want to do. So for example, if I want to do add, I know it by heart. I have a list of which instruction is with. For example, if I want to do add, it's this lever, and then I can add. For example, the input now, these are the 16 inputs, so 8 on this side and 8 on this side. Currently it's 3 plus 2, and we have 3 and 2, and we have add selected, so we get a 5. 3 plus 2 is 5. So we can see that that's working. Well, it's a bit intimidating to see, but I can go through it pretty easily. First, the first operation we can choose from is XOR. We already talked about XOR in the beginning. It is a logic gate, and we can just power it. It's blocked here, so we can unpower it if we want to use it, and then it goes all the way through the output. Second operation is the AND gate. It's a bit of a weird state because it needed to be compacted, but it works the same as in the beginning, and it also is blocked. So if we want to use it, we unblock it, and then the signal can continue to the output. On this side, we OR the lines together. What OR means is you just combine the 2 signals. So if, for example, if one of the 2 is on, the output will be on. If the other one is on, the output will be on. And also when both inputs are on, it will be on. So they're basically just wired together, and it goes all the way through the output. It's blocked over here, and it goes through the output. Notice there's an XOR gate over here. This is very necessary, because what happens if you only have one input on the XOR gate? It just passes through. But if the other side is powered, it's powered, and only if this one it turns off. So this is basically an inverter, so it's 2 functions in one line. One, it's an OR gate, and the other one, it's an inverter, so we can invert the signal that's been put in. Then the most important one, the middle part over here, this is the adder. It adds 2 numbers in binary. with two inverters in before it. If you, let's say this is input A and this is input B, if you invert B and just put it in and add 1, you're basically doing binary subtraction. So that's also, we can use that's cool. So we can use an adder for subtraction, which is very nice because it saves a lot of space. Finally, I'll talk about this side over here. This is a bit shifter, and you know, it is in the name, it shifts bits. So here it is. For example, let's say you have 4 bits and this is the state, so 1 0 1 0. If I shift, this one will move over here and this one will move over here. Now we have shifted the bits. And what happens if we shift it again? This one goes all the way around over here and this one goes over here, and now it's in the original state again. And this just shifts over and over, and that's why this machine is here. Now we move on to the program memory. That's the entire middle part of the computer. Of course, here we got the clock. The clock just moves in infinite circles and circles. The output of the clock goes into the program counter. The program counter counts up by 1 every input it's gotten. So that's 2, 3, and 4, and that just keeps going. The output of the program counter goes into this purple part. This decodes the signal. So for example, now a 4 has been inputted in binary, so the fourth, how it's called, the fourth instruction is being powered, depowered, so the instruction can do. How does this program memory work? Well, it works by putting torches on the side, and when it's unlocked, the torch will power and the signal will go through and into the machine. These colors are not for show. The yellow part goes in the input from the register, the purple part goes on the input from the ALU, orange part is the input from the clock, the purple, green, white and light blue part on the bottom here are for the bottom inputs of the register, and then we got the red lines for the screen and the clock, just some control lines. Then we'll just quickly talk about the UI. I chose this spot because you get a nice view of the screen. That's just nice to have, like a view, and we get access to our inputs. Well, the only inputs I currently have, which are the only ones that are currently necessary, is the numbers. These numbers are go through wires, they wrap all the way around, and they go into the registers. And this includes the register commands. For example, you can grab the location and you can write. These dark green lines, they go all the way around as well, go to the bottom and go into the input of the register, and they write if you ask for the number. For example, I can grab 128 inside of register 4, and then I can write. Now I wrote a 128 register 4, so we can go to our register, we can search for register, and we can see a 128 has been stored inside of the registers. Very nice. And now that we have explained the basics, like the parts of the computer, it's time to take a good look at the computer. Let's just see how big it really is, because it took a very long time. Well, this is the computer. It's a bit messy. We can see all the parts. We got a program memory, we got our register, we got our ALU, we got our through. The entire part of here, this is the display. I skipped it for this video because it's kind of irrelevant to the computer itself, but you need it to display what the computer is doing. So yeah, we do kind of need it. So yeah, that's that. We can see that it's pretty big compared to me. If I'm standing next to it, yeah, it's pretty massive. But yeah, I put a lot of time into this. So yeah, let's see some programs it can run. Now we'll just talk about some programs this computer can run. We'll go through this quickly because otherwise the video will be way too long. The first program I'll be talking about is an add program. So it just adds, it just counts up. So we can see now it's at 7, and then if we wait a little bit longer it should turn to 8. Just give it a few seconds because it's not the fastest computer in the world. and then we get an 8, and this just continues until the bits are up, and in this case 8 bits is 256. Well, we'll not be waiting for this, because that will take like half an hour. Well, how does the program works? First instruction, we do nothing, we just wait. Second instruction, we load a 1 into register, let's see, register 1, and we write it. Then we wait an instruction again, and then we add a 1, well, we store a 1 in register 2, and then we wait. Then we add, remember the purple part is add, we add register 1 and register 2, we store that result again in register 2, and then we loop back to instruction 5, which is add 1 plus 2. Well, remember, which is adding register 1, 1, and 2. Well, remember, instead of a 1 in register 2, there's now a 2, so it will flip to 3. And then we loop back again, and then it's not 4 plus 1, it's 5. And it just keeps going until the loop is complete. And now let's talk about another program I've managed to run inside of the computer. It's called the Fibonacci sequence. The Fibonacci sequence is pretty cool, because it adds 1 plus 1. But then then 1 plus 1 equals 2. So it stores the 2 inside of in this register. Then it adds again. So it adds 1 plus 2, which equals 3. And it stores that in this register. So now we have a 3 here and a 2 here. Then it adds them again. So now it's 3 plus 2, which is 5. And it adds it over here. Then it does it again. 3 plus 5 equals 8. So like this. And this just continues going on and on and on and on until it's done. And let's load it into the computer currently, and we can if I can just fly over here, yeah, we can see it over here. So 1 is loaded inside of the register, then we wait, then another 1 is loaded, then we add 1, register 1 and 2, then we store that again in 2, then we add register 1 and 2 again, that's and then we just put it in register 1, and then we loop back into instruction 5, which adds these two numbers together, and it just continues going and going and going. And if I can just start the clock, then you can see it counting. Thank you so much for watching this video. I put a lot of effort into building this computer. It's taken me like 2 months or something to build this thing and research everything. So I hope you enjoyed. Yeah, and I'll see you next time.